you serious? Are you serious? Okay, guys.
Vacuum of space. When light moves through things like glass or fluids, it slows down appreciably. If it didn't, things like telescopes and human vision would be impossible. But what would happen if light slowed down much more? If the speed of light were 0? Light speed is 186,000 miles per second. It is a universal constant, but a constant with a catch. It travels at that speed only in a vacuum.
Light changes its speed when it travels through different media. It travels more slowly through water. That's why you see refraction and bending and rippling of light when you're underwater.
Life as we know it would be very different if light didn't propagate at different speeds through different materials. For example, we wouldn't be able to see. Our eyes wouldn't work the same way.
In a universe where light moved at the same speed through all materials, we would know little of the world around us, seeing only vague blobs of dark and light. That's because our eyes depend on biological lenses to focus images on our retinas. Just like lenses made of glass, they work because light slows down as it passes through them.
And why is that? Because light is absorbed by the atoms of glass, and then they re-radiate it later. So there's a delay factor. Light hits an atom, the atom vibrates, and then sends the light package off. So there's a delay factor.
The delay factor also causes light to bend when it hits glass shaped into a lens. Bent in just the right way, light can be focused, collected, and magnified. For astronomers studying the universe, nothing could be more important.
Thank goodness light slows down when it goes through glass, because that's the reason why we have telescopes. The reason why we have telescopes is because light bends going through glass, and we can concentrate large amounts of light to a single point, and then that gives us the ability to see the marvels in the universe itself.
Light travels through the glass lenses of telescopes at about 124,000 miles per second, 2/3 of its speed through a vacuum. But some scientists are looking at making use of light at far slower speeds.
And then we have the AOs over here. They're pretty much all functioning now.
At her lab on the campus of Harvard University, Dr. Lena Howe has taken slow light to the extreme by reducing light speed to 0.
The speed of light, of course, is incredibly high. I mean, nothing goes faster than light. And, you know, the usual 186,000 miles per second. And we kind of thought, gee, that's awfully high. Let's try to do something about it. So we have the detector right there.
Howe and her team conducted their experiments in a complex laboratory filled with lasers, mirrors, prisms, and other exotic gear. It is a branch of physics where few have dared to tread.
If you can start to change things so dramatically as taking this enormous light speed and then bring it down to bicycle speed, that then you're in a completely new regime of nature. You're able to now start to probe areas, regions of nature where nobody has ever been there before.
The brakes are put on light speed inside Howe's lab by focusing lasers on 2 microscopic clouds of sodium gas, chilled to a few billionths of a degree above absolute 0. A control laser hitting the 2 clouds sets them up for action. Then, a quick light pulse shoots into the first cloud, where it is squeezed into the gas and slowed to just a few miles per hour.
The light pulse goes from being about 1 kilometer long in free space. It compresses like a concertina as it enters the atom cloud and ends up being only 0.02 millimeter in size. That's less than half the thickness of a hair. So really small, and it's so small that the light pulse actually ends up fitting totally inside the atom cloud.
Howe says the atomic imprint of light in the sodium cloud is a perfect copy, embedded in atoms, of the original light pulse. It can then be stopped in free space between the 2 clouds before moving on. When it enters the second cloud, another shot of the control laser expands it to its original size, shape, and speed of 186,000 miles per second. It is comparable in some ways to a science fiction transporter that sends people or objects through space.
So in this experiment, what we really do is we stop and extinguish a light pulse in one part of space and revive it in a completely different part of space and send it back on its way.
Since light can carry information, this super advanced technology points the way to futuristic light-based computers that bypass wires and electronic chips. Information read directly from light may be faster, more compact, and more secure than anything we have today. But the greatest vision of scientists and dreamers is to be found at the other end of the light speed spectrum. We still face the speed of light as an impenetrable wall, a speed that Dr. Einstein told us could never be exceeded. Yet history is packed with impossibles that have become realities. Will we ever, for instance, be able to reach the stars in ships that go faster than the speed of light? If so, when? In April 2008, world-famous physicist Stephen Hawking called on the human race to colonize space and make interstellar travel a long-term aim.
Spreading out into space will completely change the future of the human race, and maybe determine whether we have any future at all.
The stars are so far away that interstellar travel is impractical unless we can go faster than light speed. But that's an obstacle. Einstein's theory of relativity tells us that a spaceship's mass approaches infinity as it nears the speed of light.
So as you try to go faster and faster and faster, you actually get to a point where it takes more and more energy until it's an infinite amount of energy to go the speed of light. That's impossible.
It means that travel at light speed is also impossible. Or is it? Mark Millis is one of a handful of scientists who isn't ready to throw in the towel on the subject. A NASA propulsion physicist by profession, he likes to build models of starships in his spare time, and is well aware of the giggle factor in any talk outside science fiction of star travel.
The giggle factor is actually a healthy response. It helps provide skepticism to the topic, to ask deep questions to make sure that we're proceeding correctly.
Once head of NASA's mothballed Breakthrough Propulsion Project, Millis is editor of a book that has collected the serious current research on the subject.
When it comes just to the light speed issue, there's about 36 physicists who've written articles, some skeptical, some suggesting new methods on the topic.
No one is saying that anytime soon we'll be able to have warp drive to the stars. But on a scale of centuries to millennia, it can't be ruled out.
Virtually all physicists agree it's impossible to travel through space at faster than light speed. But there may be a way to cheat by altering space instead of traveling through it.
Believe it or not, even NASA scientists are studying the possibility that perhaps we can fold space, punch a hole in space, make a subway system through space and time.
That's the basic idea behind using wormholes to actually twist space around on itself and take a shortcut through the universe. What would a wormhole machine look like? Probably huge in scale, with equipment staged perhaps on a massive number of asteroids arranged in a gigantic sphere.
It would require an enormous battery of laser beams to concentrate tremendous energy to a single point. You have to attain fantastic temperatures, the highest energy attainable in our universe, in order to open up a hole, a bubble, a gateway perhaps to another universe.
Another way of tricking space into letting us travel faster than light is the warp drive.
Miguel Alcubierre was the first one to write about the warp drive in 1994.
Alcubierre, a Mexican physicist, worked out the math for a starship propelled by warping space-time itself. Behind the ship, space-time is expanded. In front of the ship, space-time contracts. In between, the ship rides like a surfer. The ship itself sits inside a bubble, and the space around it pushes it faster than light. A successful warp drive, if it is possible at all, is probably centuries away. But in Switzerland, physicists at the Large Hadron Collider may be headed in the right direction right now.
Now, the Large Hadron Collider is an atom smasher. It's a particle collider. But it's going to get to high enough energies that space and time will actually warp and bend. We're actually practicing how to bend space in the laboratory. It's the first baby step toward a warp drive.
With the physics we now know, we won't travel faster than light speed in the foreseeable future. That doesn't mean we shouldn't try.
Even though light speed travel might turn out to be impossible, to give up without trying is just giving up.
Outside his work at NASA, Millis has founded the nonprofit Tau Zero Foundation to encourage serious research on star travel. Although few scientists are pursuing the idea actively, many agree it's worth at least the effort.
Understanding our universe is one of the most basic needs human beings have as an intelligent species. So should we pursue technologies or physics that might allow us someday to travel faster than light? Absolutely. Because we never know where this might take us. Even though we might never discover a way to travel faster than light, we might discover a whole bunch of other very useful things.
And what if science ultimately proves the light speed barrier is...
I'll see you guys at 12 noon Eastern today on the coming apocalypse. Give your life to Jesus Christ, because these are the prophetic signs that the Bible said would come. Earthquakes in divers places. Are you serious? Are you serious? Okay, guys.
Vacuum of space. When light moves through things like glass or fluids, it slows down appreciably. If it didn't, things like telescopes and human vision would be impossible. But what would happen if light slowed down much more? If the speed of light were 0? Light speed is 186,000 miles per second. It is a universal constant, but a constant with a catch. It travels at that speed only in a vacuum.
Light changes its speed when it travels through different media. It travels more slowly through water. That's why you see refraction and bending and rippling of light when you're underwater.
Life as we know it would be very different if light didn't propagate at different speeds through different materials. For example, we wouldn't be able to see. Our eyes wouldn't work the same way.
In a universe where light moved at the same speed through all materials, we would know little of the world around us, seeing only vague blobs of dark and light. That's because our eyes depend on